Greetings everybody. So I want to show you this problem about calculating a Riemann sum based on partial information about a function. But before I do that, there's something I posted right here that's more general about Riemann sums. And I think it'd be good if you saw that before you see what I have to say here. So either watch that one, or if you already learned something about Riemann sums somewhere else, then that would be good. All right, but I don't want this to be the very first video or information about Riemann sums that you have. So let's get into it. So I say that I have partial information about a function because it says that there's a car moving, and all this table tells me that at various times I know the speed or velocity in miles per hour. So at the 0.5 hour mark, at that instant, this object is moving 50 miles an hour. Okay, that's the kind of information we see in this table. I say this is partial information because sometimes we have a formula for a function where I can give you any time, pick any number that could be a time in the domain of that function, plug it in the formula, and get, say, the velocity in miles per hour back. I don't have that here. I can only tell you the velocity at times 0, 0.25, 0.5, and so on. Okay, so if you wanted to know how fast this object was moving at time 1.8, that's not on the table. Maybe I can make a reasonable interpolation from that and tell you, but it's at least not there. So I don't have total information about this. Okay, so I'm just going to do part B. Part A asks something about the graph, and I'm not too worried about that. I'll talk about part A along the way anyway. Let's do part B. It says find the midpoint Riemann sum approximation to the displacement on the interval 0 to 2 with n is 2 and n is 4. So here's what's happening there. This interval 0 to 2 is the interval for time, or the independent variable, which I have my earliest measurement at 0 and my last measurement at 2. And what I can do is I can divide that interval up into either 2 equal parts, which you see here, which I'm going to do first, that's n is equal to 2, or 4 equal parts, which I'll do later. So look at this. If I were to divide this interval 0 to 2 for t into 2 equal parts, it would be like one part would be 0 to 1, and then the other part be 1 to 2. Okay? The sample points, those are the midpoints of each of these intervals. So like from 0 to 1, the midpoint of that is 0.5. From 1 to 2, the midpoint of that is 1.5. Those are the sample points. I know I'm doing it that way because it said find the midpoint Riemann sum. So the sample points can be found in any number of ways. They just exist between the partition numbers. But if you want them to be the midpoints, there they are. Those are the midpoints. Okay, so I need a partition. All right, 2 equal parts on my interval. That's how I'm doing it here. Those were the instructions. Sample points, okay, those are the midpoints. And then I need some function to do calculations with. That function is velocity is a function of time, which remember I don't have except for the data points on these tables. Okay, all right, so here's the Riemann sum. Here's what you do. You take the distance from 0 to 1, which is 1, and then you take the sample point and put it into the function. That first sample point 0.5, and then you take the next distance from 1 to 2, that's 1, and you take the next sample point and put it into the function f of 1.5. And then you calculate that 1 times f of 0.5 plus 1 times f of 1.5. Now, where do I get f of 0.5 and 1.5? Remember, I don't have a formula for this function. How do I evaluate it? That's on the table. F of 0.5, when t is 0.5, the velocity, the function value is 50. And at 1.5, it's 30. So notice that's what I put in here after I wrote it out. It's 1 times 50 plus 1 times 30, and that's 80. Okay, now that's, believe it or not, I think the short story on what the Riemann sum would be in this case. But I think you could understand it better if I told you what the partition and sample points and the function do in this Riemann sum. Like, well, how do they work together? Why do we find them like this? Why do we multiply and so on like this? What's the whole rationale behind it? So think of it this way. So at this point, I will actually draw a rough sketch of that function where velocity is a function of time. Okay, I drew this with the ruler and I measured everything out, so the scale is good on it. It looks like this. And what the partition does is divide this interval on the horizontal axis with the independent variable into two rectangles. On this graph, this curve where velocity is a function of time, I'm going to impose two rectangles of equal width. Okay, so when this says n is equal to 2, well, just imagine that we have our partition on the x-axis, horizontal axis, into two rectangles. The first one would exist from 0 to 1, and the second one from 1 to 2. Okay, the sample points are the midpoint of each rectangle. There's one of them at 0.5, one of them at 1.5. Now, a rectangle has a width determined by the partition and a height, which is determined by the sample point on the curve. So this first rectangle may have its width from 0 to 1, but its height is determined by that sample point 0.5, which is what? It's the function value at 0.5, which is 50. So that's how tall that first rectangle is. It's 1 unit wide and 50 units tall, imposed on my curve. The second one exists from 1 to 2. Sample point for it, 1.5, right there at the midpoint. How tall is it? Well, what does 1.5 give you on the curve? It's 30, so that's the height of the second one. Now, this is how we found the Riemann sum, right? So that was just on this slide over here. Well, so 1 turns out, you know, when I had a 1 right there, that's the width of that first rectangle, okay? And the function value is its height, determined by the sample point. And then I add. And then this 1 is the width of the second rectangle, which happens to be 1. And this function value is its height. So that what we were doing over there was finding the area of this rectangle and adding it to the area of the next one. That's what the Riemann sum does. Now, another way to look at it is, well, since the horizontal axis is time and the vertical axis is velocity in miles per hour, then I could also see that that width of the first rectangle, it has that geometric interpretation. It is a rectangle, and that is the width. But if you say, well, that was the time axis, then that's a length of time in an hour. And this function value, what was that? Well, that's a velocity, 50 miles an hour. And then that next one, that's a length of time in hours. Or you could see it as the width of the second rectangle, but it's also a length of time in hours. And then that function value, well, that was the velocity at 1.5, which is 30 miles per hour. So what do you get then? Now I have a whole new interpretation of this number, 80. What do you get if you multiply a time times a rate? You get distance. The times cancel, you get 50 miles. Same thing here with this next one. The times cancel, you get 30 miles. So I could say, well, the Riemann sum might be 80, but specific to units, it's 80 miles. What the Riemann sum does, you could say, is it assumes that the speed on this first hour was constant at 50 miles an hour, even if that isn't true. And it assumes the speed on this second hour is 30 miles an hour, even if it isn't true. Why do we assume something that's not true? Well, because this gives us a rough way to calculate how far the object has moved, 80 miles, okay? I mean, all I have really is distance is rate times time. And the rate's not constant. Distance is rate times time only applies if the rate is fixed, if it's not changing. So we make some assumptions here and we say, well, okay, suppose for the first hour it is constant at 50. And for the second hour it is constant at 30. Then I get at least a rough estimate. Okay, so yeah, that Riemann sum could tell me two things. It could be an approximation of the area under the curve. Those rectangles are trying to measure the area under the curve, or the distance the object has moved over the course of 2 hours. Okay, now this seems very much like an approximation. If this Riemann sum is trying to measure either the area under the curve or the distance the object moved, it doesn't seem like it's doing a very good job. It overmeasures quite a bit here, and it undermeasures quite a bit there. How could we improve on it? Is, well, why stick with two rectangles? Why not put more of them? The more rectangles I have here, the more these over or under measured areas are going to squeeze out. It'll be better. It'll be a closer approximation to whatever the truth is, the more rectangles you have, okay? So that's why the other part of part B is let there be four rectangles. Now I didn't draw that one, but you could use your imagination that if there were four, they would cover this space more accurately and give me a better approximation, okay? All right, so here's the partition dividing the space from 0 to 2 into 4 equal parts. Now, if I want to, I can imagine those as 4 rectangles standing on the horizontal axis. And then here are the midpoints, okay? The Riemann sum is the width of the first interval times the function value at the sample point plus the next one, plus the next one, plus the next one. And I find all of that information either by the function, if it's given as a formula, which is not this time. If it was given as a formula, I'd put 0.25 into that formula and I would get the number that's supposed to be there. In this case, I only have the data on this table, okay? So I have to make use of that, but I can look up every one of these and I get 95 miles. All right, so that's how Riemann sums work, and that's how we can understand them beyond geometry. Yes, it does try to tell me the area under the curve, but in this case, if I look at the units of what I'm working with, it tells me something else. It tells me how to go from information about how fast an object's moving to how far it's moving, okay? Now, if you were to see other problems other places, the partition and sample points could be made different ways. They could be random. It doesn't mean that every interval here has to be the same. In this problem, that's what's intended. 2 intervals, each with a width of 1, or 4 intervals, each with a width of 0.5. Also, the sample points can be anywhere within those subintervals. This one, it happened to say, let it be the midpoint, but it could be different. Nonetheless, if you're going to calculate a Riemann sum, some information must be given to you about how to derive the partition and sample points, but once you have that, you can do it as you see in this video.